Good morning. Today's subject is computer graphics and visualization. Today we will be understanding about 3D geometric transformation. Introduction. Myself, Abhimanyu Pal, 1V20CS001. I'll be facilitating today's session. The goal of our session is to know about 3D geometric transformation. Today's agenda. Detailed explanation about 3D geometric transformation. So let us begin with the session. Are you ready, guys? What is 3D geometric transformation? Geometric transformation refers to the process of manipulating the position, size, and orientation of object in a 3D-dimensional space. These transformations are fundamental in computer graphics, computer-aided design, that is CAD, and other fields where 3D modeling and visualization are involved. Some of them 3D geometric transformation include transition, rotation, scaling, shearing, reflection. It will provide a brief overview of the transformation as shown in the figure. So let us know about these points. First is transition. It involves moving an object from one position to another by adding a constant vector to its coordinates. In 3D space, transition is performed by adding the same offset value of x, y, and z coordinates for each point. Transition in 3D can be represented using a 4x4 transition matrix denoted by T. The transition matrix looks like the following figure, where it is represented by 3T. Here we can see 100dx, 010dy, 001dx, 001. The dx, dy, and dz represent the transition amount in the x, y, and z direction respectively. To apply the transition to a point P of x, y, z, we apply the transition matrix T with the points with coordinates p, 1 as shown in the figure, where p dash is equal to t into p, 1. Now let us know about rotation, which is the second point of our 3D transition, 3D geometric figure. Here, rotation transforms an object by changing its orientation around a specific axis or point. In 3D, rotation can be performed around the axis x axis, y axis, and z axis, as well as an arbitrary axis defined by vector. Rotation are typically specified by angles or matrix. Rotation in 3D can be represented using rotation matrix. There are different rotation matrices for rotation around the x-axis, that is Rx, y-axis, that is Ry, and z-axis, that is Rz. Each rotation matrix is a 3x3 matrix. The rotation matrix looks like the following figure. Here 1 0 0 0 cos theta minus sin theta, 0 sin theta, cos theta. Here theta represents the angle of rotation. To apply a rotation to a point P of x, y, z, we can multiply the rotation matrix R with the point homogeneous coordinate p, 1, which can be shown in the figure. P dash is equals to matrix P dash is equals to R star p, 1. So let us move for the next point, that is scaling. Here the scaling modifies the size of an object from the x, y, and z axis. It involves multiplying the coordinates of each point by scaling factor. Uniform scaling applies the same factor to all dimensions, while non-uniform scaling allows different factors for each axis. Scaling in 3D can be represented using a 4x4 scaling matrix denoted by S. The scaling matrix looks like here. Here we can see in the figure Sx 0 0 0 xy 0 0 0 0 xz 0 0 0 1. Here Sx xy xz represent the scaling factor along the x, y, and z axis respectively. To apply scaling to a point P of x, y, z, we can multiply the scaling matrix S with the points homogeneous coordinate p, 1. Here the resultant we can be as follows. P dash is equals to S star p, 1, where B dash is the resultant matrix, and S is the scaling factor. So let us move to the other points: sharing and reflection. Sharing transforms an object by shrinking or sliding along one or more axes. It can distort the shape of an object by displacing points in a particular direction based on their initial coordinates, whereas refraction flips an object across a plane or an axis, resulting in a mirror image. In 3D, reflection can be performed across xy plane, yz plane, and zx plane, or any other plane defined by a normal vector, as we can see in the figure. So let us conclude our session. This transformation can be combined and applied in a sequence to achieve more complex effect. In a computer graphics, matrices are often used to present and perform this transition efficiently. By applying appropriate transformation to the vertices of 3D object, it becomes possible to annihilate, manipulate, or simultaneously various scenarios in a virtual environment. Thank you guys. Have a nice day.